forward to the cloud. It is a great pleasure to welcome home Jeffrey Meier, who will tell us about trisections as singular branch covers.
Okay, well, thank you very much to Dave for the invitation, and thank you to everyone for coming to listen today. Yeah, so I'm going to talk about sort of how I have come to understand branched coverings in a fairly general sense over the last couple of years. The main focus of this talk will basically be on this paper with Ryan Blair, Patricia Kahn, and Sashka Kuchikova, where we show that certain trisections can be realized as threefold simple branch covers over bridge trisected surfaces, as long as we allow singularities. So before I tell you exactly what that result says, I just wanted to throw up a couple of classical theorems to motivate the study of branched covers. And so maybe there's a little something for everyone here. So sort of probably one of the better known results is that every three manifold is a simple threefold cover over the three sphere. And later on, this was pushed into dimension 4 by Iori and Piergalini, who showed, I guess I don't state it here, but they showed that every four manifold is a simple fivefold branch cover over S. Oh, that's supposed to say S4. That would be quite a result. Okay, fix that. 4. And they can get to be a fourfold cover if they allow the branch locus to be immersed. And so a similar, another result in this vein is this great theorem of Aru that was improved by Aru and Kartsakov, that says every symplectic four manifold is a simple branch cover over CP2. And here the branch locus is immersed and also has cusp singularities. And then I sort of just included this last result just to sort of head off any questions about how general this can be. There's this old work of Berenstein and Edwards that gives obstructions to the existence of branched coverings. And this work is very general. They're working sort of just with very few restrictions on the branch locus, other than it be sort of locally flat. And so what they show is that there's no possible degree n branched covering of the n torus over Sn. Sorry, any branch covering is at least degree n. And then they give this kind of interesting example of the non-existence of a covering of degree n, or sorry, degree, I guess. Oh, I think I messed up my dimensions here. This should probably say 8n. I messed up my use of the letter n. Yeah, anyway, so they give this sort of funny example with using a quaternionic space to show that they're not even examples sort of in this optimal degree where the branch locus is embedded. So I kind of just wanted to throw these up here to give you a flavor of how people think about these branch covers. And I think there's sort of the general idea is people are interested in producing these branch covers, and they're interested in studying sort of what the possible degrees are. And they're also interested in studying what characteristics the branch locus has to have. And so it's sort of in this context that we started thinking about trying to realize simply connected four manifolds as actually threefold branch covers. So here's our main result. And then I'll basically just spend the rest of the talk setting up some classical machinery and talking about branched covers. And then hopefully if there's time, I'll conclude with a sketch of the proof. So the idea is that we want to restrict our attention to trisections where one of the four-dimensional pieces is a four ball. So that's what this 0 here gives us. And what we're able to show is that we can actually realize this trisection as a threefold simple branch covering over the standard genus 0 trisection of S4. And the branch locus can be arranged to be smoothly embedded away from a single point where it's the cone on a link. Okay, so you should think of some smooth surface in S4 with maybe a one with a boundary given by a link, and then you just take that boundary and you cone it off to a point. And that's the sort of branch locus that we're producing here. And everything sort of respects the trisection structure in a really nice way. So this branch locus will be put in bridge trisected position with respect to the trisection on S4. And once we arrange that, then the trisection on S4 will pull back to the trisection that we're given. So maybe there's some, maybe it's not exactly clear a priori what this means, but maybe it's obvious that it should just mean all of the relevant pieces get, the branch cover restricts to branch coverings over all of the relevant pieces of the trisection. And then maybe I'll just mention sort of a second piece that came out of this is, it's not clear to me if this is an improvement, but maybe some people will think of it sort of as an improvement. If we further know that another parameter is 0, then we can swap out this cone on a link for 2 cone points on knots. And so maybe this is sort of desirable in some way. And maybe I'll just say, what's sort of the point of these trisection parameters? Well, the goal here would really be to say something about simply connected 4 manifolds. And 4 manifolds that admit trisections of this type are simply connected 4 manifolds.
So what do? Do you just take like a Haggard-Kirby diagram representing the G, K1, K2, 0 thing, and you put it in bridge position with respect to the sphere, and then voila, it all works out?
No.
It is more
complicated. Made for a shorter talk.
Yeah, okay.
No, what we'll do is we'll start with the branch covering over the cores of the trisections, and we'll extend it outward over all of the pieces in a sort of systematic way. And there'll be 1 or 2 hiccups that we have to overcome, but everything goes through fairly smoothly. And then I sort of I listed the way the Euler characteristics behave down here, if you want to sort of, you can kind of get an idea for, if you do change from a singularity being a cone on a link to 2 cones on a knot, then there's sort of an expected change in the way the Euler characteristic of the branch locus is related to the Euler characteristic of the manifold covering it. Okay, so the other thing I was saying is it's sort of an open conjecture whether every simply connected 4 manifold admits a trisection of this sort. And this is related to the question of whether every simply connected 4 manifold can be built without, say, 3 handles. If that were the case, or equivalently without 0 handles. If that were the case, then you could construct a trisection of this sort and realize that simply connected 4 manifold as a 3-fold cover. So the question of realizing simply connected 4 manifolds as 3-fold covers over the 4 sphere is related to the question of whether simply connected 4 manifolds admit handle decompositions without, say, 1 handles, I guess.
I have 2 questions.
Okay.
So one is, do you have any idea if just simple 3-fold branch covering with branch locus as you described implies simply connected? I don't know why, I can't see why that was clear, but maybe.
Well, sort of yes, for a silly reason, which is the only way we're able to talk about branched coverings over singular surfaces is by requiring the link of the singularity to have a cover that's the 3 sphere, because we'd like the cover over the cone to be the cone of the cover.
Okay.
And so if we want to get a manifold upstairs, then we better be coning on the 3 sphere. So what sort of falls out of this is that one of our sectors will be a 4-ball covering a 4-ball. But I guess the answer to your question though is no, because
you strip the trisection data.
If you strip the trisection away, yeah, I guess that's a good question. I don't think I know any reason why the cover should have to be simply connected.
And then the
It's probably not true.
And then this like possible improvements, trading a link for 2 knots, 2 cones on knots. I mean, you could imagine the knots could be like a zillion times more complicated than the original link. Is there a little bit more to it, like control that or any complexity?
I mean, how much the restriction of what you have is that that the branch cover has to be S3, right? I mean, that's
It's not super restrictive, as we'll
not.
see. No, there are lots and lots and lots of links that have threefold covers S3.
And
Which
how
is sort
about
of one of the surprising things about irregular branch coverings, in my opinion. Yeah, that's one of the things I wanted to sort of make clear in the next few minutes. Okay. Yeah, I don't know if it's an improvement. I mean, maybe some people like to think about embedded surfaces with singularities, which if you have a cone on a link, it's maybe not really fit that bill.
why not? Why do you say that doesn't fit the bill?
Well, I don't know. I kind of think of like a singularity on a link as a self-intersection. Like if the link were a hop link, it's sort of like a generic self-intersection, not as much, the cone on the hop link is maybe better thought of as a transverse self-intersection rather than.
I mean, but those are singular surfaces, right?
Sure. Yeah.
So maybe I
Yeah, but
misunderstood.
somehow a bunch of surfaces intersecting transversely at points is a lot nicer than some surfaces with cones with cone points, which are cones on knots, right?
Yeah.
If the only singularities you have is cones on hop links, that would probably be about as good as you could possibly hope.
Yeah, and just to harken back to the first page, that's exactly what Iori and Pirgolini prove in this setting, is that they can assume that their surface is smoothly immersed with generic transverse intersections. Okay, yeah, you're right. I mean, I'm not gonna, I'm agnostic as to which one of these versions is better. If you have a preference, then I'm happy to respect that. Okay, so also I guess I wanted to ask, can people see this okay, or should I zoom in so that only some of the text is?
My old eyes would prefer if you zoomed in a bit.
Okay, that was sort of my plan, so I'll do that now. Okay, is that a little bit better?
Better.
I don't want all of the stuff to be showing up anyway. Okay, so I just wanted to let everyone know that Daniele Zudas has this really nice tesi where he talks about branched coverings in a really general sense, and I would refer anyone who wants to sort of just get the rundown on how to think about branch coverings of manifolds to just read this chapter 1 of his thesis. But here's like I want to just set up some basic terminology and give you the idea. I mean, this picture sort of tells you exactly what's happening with the branch covering, and it really is safe just to think about surfaces for now. And I think my motto is sort of that it will continue to be safe to think about surfaces forever. So, even though this can be defined in terms of sort of like maps of n manifolds, I think it's a lot easier to think about it just in terms of branch covers of surfaces along points. So the local model is we have a disk with a point y in it, and then it's covered by some disjoint union of disks, each of which sort of looks locally like this map, z to the n. Z goes to z to the n, this winding map. And so to each point in the preimage of y, we can associate some sort of local degree. And this just tells you how much you're winding at each of these points. So the example that I've given here, sort of this local picture is degree 3, and this local picture is degree 2. So the total, what happened here? Yeah, so the total degree in this case would be degree 5. Okay, we add them together. And this is sort of exhibited by paying attention to the green dot. So the green arc and the green dot just are sort of help visualize the parameterization here. So we have these, over every point in over every sort of value, we have all of these pre-images, and we get these local degrees, which we can then add together to get the total degree of the covering. And the local degree is going to be locally constant over components of our branch locus, and the total degree is going to be globally constant. And an interesting sort of piece of information that we can get out of a branch covering is this partition of the degree given by the local degrees above a point. So if we have just some regular value, then this partition will just be a partition with all ones of length d, right? 1, 1, 1, 1, 1. But over a branch point, it will have some sort of more interesting characteristic. And so to a branch cover, we can sort of associate a partition of d to every point in the codomain, and if we throw out the sort of regular points, which are not interesting, we get this sort of finite list of interesting partitions of d. And I'll explain in a minute why this is a useful piece of data to keep track of. Okay, and then just some terminology. This doesn't end up actually being so important, but I'll just sort of distinguish the branch locus from the ramification locus by saying that the ramification locus is sort of like the interesting points upstairs, and the branch locus is the interesting point downstairs. And one thing that's important, I guess I don't say this yet, but we'll see it in a minute. One thing that's important to remember is that the ramification locus is not the same as the pre-image of the branch locus. So you can have, if I have some critical value in n, or sorry, if I have some critical value in my in n in my branch locus, then it can be covered by points upstairs that have winding number greater than 1, and also points upstairs that have winding number equal to 1. Okay, so in particular, this partition could have some values that are bigger than 1 and some values that are 1. And we'll see that in an example in a second. So an important thing to keep in mind, let's see, maybe I'll just, sorry, I'm zooming, is this notion of the monodromy representation that corresponds to a branch covering. So this is just a map from the fundamental group of the complement of the branch locus to some symmetric group. And this captures all of the information of the branch covering. So the parameter d of the symmetric group that you match into is the degree of the branch covering. And so for each meridian curve in our for our branch locus, we can consider its image under this representation, and we can split that in as a product of cycles. And the splitting of this image of this meridian as a product of cycles corresponds exactly to the local degrees of the of that point. So this is what I was sort of saying up here. You could think of the image of, if you look at this meridian for y here, just the boundary of a disk neighborhood of y, one possibility for the image of this meridian in the symmetric group on 5 symbols might be the product 1, 2, 3, and 4, 5. And this would correspond sort of precisely to having a pre-image of local degree 3 and a pre-image of local degree 2, because it's a product of a 3 cycle and a 2 cycle. So sort of all of the interesting topological behavior of the branch covering is captured by this monodromy representation. So there's an algebraic side of branch coverings, which as I'll sort of highlight on the next page, it includes actually some interesting open problems.
So if it's simple, then the meridians are all cyclic, right? And the pre-image is connected, is that right?
So the no, simple.
What does simple mean?
Simple means that the each meridian goes to a transposition. So in particular, the pre-image of a point under a simple branch covering will have sort of d-1 pre-images. 1 of order 2, and then a bunch of order 1. d-1 or d-2 of order 1 or something.
Okay.
Okay, so this was just sort of like a quick rundown of branch coverings. Next thing we'll do is sort of just look at some examples. Are there any questions at this point? I know there was kind of a lot of
okay, so this definition did not include the case where the branch locus has singularity, right?
No, it didn't. That's right. Yeah, this definition sort of includes, it sort of restricts to smooth branch locus. Yeah.
So like a cyclic branch cover is not a simple branch cover unless it's twofold.
Exactly. That's right.
And is simple somehow related to generic or no? I'm sorry. Yeah, I just
I don't actually know. Sashka, do you know if branch covers are generically simple?
Yes, I think that's a Bernstein-Edmonds result.
Okay.
That simple branch covers are dense in the space of branch covers or something like that.
So maybe there's some sense in which you can sort of perturb this up here and this will split into two.
Yeah, I think that's right. Yeah.
Okay, yeah, good question.
thanks.
Glad Sashka's here.
Seemingly.
All right.
Yeah,
Okay,
sorry,
so
can I clarify just a little bit? So the monodromy representation is you take a basically at the branch locus, you take a normal disk and then you consider the monodromy on the ball or on the sphere. So this S alpha, I think I maybe missed the definition.
Well, the
S-
branch locus is coded
SD.
too, right? In this.
It's permutation on a pre-image of 1 point.
Oh,
yeah, so this permutation here, yeah, exactly. It's only well defined up to conjugation, and it depends on sort of a choice of numbering the
okay, I see.
the pre-images over a point of a regular value in the neighborhood. So if I labeled these 1, 2, 3, 4, and 5, then those would be sort of the 5 pre-images of the regular value, and the sort of loop in the fundamental group corresponding to mu y sort of corresponds to permuting these pre-images. It lifts to arcs connecting these pre-images in this way.
Okay, yeah, I understand now. Yeah, thanks.
Okay, great. All right. Good questions. Thank you. Okay, so let's just look at some examples here. And I think I left this as an exercise. So the idea here is to just stare at these and try to determine what the monodromy representation might be for the points y1 and y2. So these things down here still look like disks, but now I'm sort of thinking of the entire space as being a disk, all of n as being a disk, rather than it being some local model, as I was sort of thinking in the previous slide. Okay, so maybe I'll just let you think about this for a second. But like we saw on the previous, answering Weiwei's question, we want to sort of number the pre-images of a regular value in order to sort of pin down the monodromy representation. So if I number these, let's see, I guess 1, 2, and 3, then what I see is that the image of the meridian of y1 could be conceived as something like the transposition 1, 2, and the meridian y2 would then be 2, 3. And I think the way to think about this is that if I look at sort of a, let me get a color, or maybe, yeah. If I look at sort of like maybe this is my base point, I don't know. If I look at sort of a loop here around y2, in sheet number 1, where this point, the purple point 1 is contained, this lists to a loop. And so that's sort of telling me that the monodromy representation of this meridian should fix that parameter in the symmetric group. And so what we see in this case is that this sort of so this is a representation onto the symmetric group on 3 letters. Okay. And this is also known as a dihedral. Well, this group is a dihedral group, and so this is also known as a dihedral covering. Although kind of like the only simple cyclic cover is degree 2, the only simple dihedral cover is degree 3. So I think the real generality of what we want to be thinking about is in terms of simple branch coverings. And then the answer over here is actually similar. These also get mapped to 2, 3, and this gets mapped to 1, 2. So we also have another representation into the symmetric group. And I guess in order to carry this out, I would need to pick some numbering here. I think this should be 1, 2, 3, something like that. And the dotted line, yeah, go ahead, Dave.
It's slightly confusing because, oh, sorry, I was gonna say they have the same, but there are 3 generators now for, you have a Y2 and a Y1, a Y2, and a Y3 in the last 2 things. Oh, I got it. I'm sorry, just being stupid.
Yeah, so I mean, somehow the kernels are different, right? Like you're going from the free group on, so the fundamental group on the left is the free group on 2 elements, and this is the free group on 3 elements, and they're both surjecting the same group. So you get different kernels, and that corresponds to the different topology that you're getting upstairs. But by the way, so yeah, go ahead.
Oh, okay, you're just drawing the different dots to show that it's only defined up to conjugation though, right?
Yeah, so the dots are just to kind of pictorially guide the intuition of how this cover works. And the other thing I was going to say is the dotted lines are also like useful in understanding how these covering works, but they're more than useful because if you actually cut the bottom manifold up along these dotted arcs, and then you take 3 copies of the cut open thing, then you can assemble those upstairs according to the monodromy representation and determine the space that's covering upstairs. So that's how you might actually draw pictures of these covers, given the monodromy information of the branch locus downstairs. Okay. Yeah, and I just want to focus on this example on the left again, because I think this is sort of really key in for this talk, which is that, you know, this is a branch covering of the disk to itself. Actually, I guess maybe that's not so surprising, but because that's sort of what cyclic things do anyway. But anyway, the fact that this is a covering of the disk to itself is going to be related to the fact that there are knots, which there are coverings of the 3 sphere to itself branched along knots, which doesn't happen with cyclic branch coverings. Okay, anyway, so I'll just finish by sort of stating 2 things. One is sort of this very useful formula to keep in mind, the Riemann-Hurwitz formula, which actually lets you calculate the Euler characteristic of the cover in terms of the local degrees. Okay, and so you know, this is really useful in sort of pinning down the topology of the object upstairs. And then the other thing I just wanted to state, just sort of for historical completeness, is that there's this really old problem that was posed by Hurwitz in 1891, which basically asks, you know, if you remember, if you take these, remember these AIs are these sort of the partitions corresponding to the local degrees over each critical point. And so if you take the data of your branch covering, so the data of your branch covering here is going to be some closed surface, and then n branch points, and then the local degrees according to those branch points are going to be these partitions of some fixed value d. And so there's this question of, is there a d-fold cover that realizes this branch data? And this is still an open problem in many cases. So there are some cases that are known, but I think even the case of branch coverings over the sphere is still open. And of course, there's an algebraic side of this, right? This is a question about finding representations, certain representations of, I guess in this case, free groups into symmetric groups. So anyway, I don't know too much about this, but I wanted to mention it because I think it's pretty cool that there's still things that are unknown about even just something as simple as branch coverings of surfaces. Okay. Any questions? I haven't been looking at the chat, but I'll take a look right now.
Try to monitor the chat too. I don't think there was anything.
Okay. All right, so here's where I think things sort of start to get a little bit interesting for me, which is the following sort of immediate proposition, which is that if we have a branched covering, and any branched covering, where the bottom manifold is a handle body, three-dimensional handle body, and the branch locus is a trivial tangle, then the covering manifold will also be a handle body. Okay, and the proof is very simple. It says, think of your handle body. Maybe we'll focus on this left picture. Think of your handle body as a surface with boundary cross I, and think of your trivial tangle as points in that surface with boundary cross I. So this is one characterization of trivial tangles, and we know sort of that the branched cover. So now the branched covering is just going to be the branched covering of the surface cross I, and we know the branched covering of the surface will give us a surface with boundary. And so the thing that we're getting upstairs is also going to have to be another handle body. Okay. Does that make sense? Okay, seeing some nods. So for me, this is starting to get pretty interesting now, you know, because I care a lot about trivial tangles and handle bodies. And so what this, oh yeah, so Sasha keeps sending me private text messages in the group chat that no one else can see. But she said, what's a trivial tangle in S2 cross D2? What that?
S1, sorry, S1 cross D2.
Oh yeah, so okay, so like, what's a trivial tangle in like in a general handle body versus in a ball, you mean?
Yeah, sure.
Yeah, it just means that the arcs of the tangle can be isotoped simultaneous to lie in the boundary. Although, you know, maybe if I just wanted to be very economical about it, I could define a trivial tangle as points in a surface with boundary cross I. Then this would be immediate. And that's actually an equivalent definition for a trivial tangle.
Okay.
Just like a trivial tangle in a ball is homeomorphic to a disk with points in it cross I, if you sort of straighten everything up. Okay. So so the connection between handle bodies and branch coverings gets even more useful. So I stated this theorem on the first page, that every three manifold is a threefold cover of S3 branched along some, in fact, branched along a knot. And moreover, it's actually true that the Heegard splitting data of a given three manifold can be tracked through this covering. So instead of just thinking about a three manifold, think of a three manifold with a fixed Heegard splitting. You can actually realize that Heegard splitting as the simple threefold cover over a bridge splitting of a knot. So this could actually even say knot. Maybe I'll change it. This is actually of a knot in S3. Okay. All right. Okay, so how do we want to think about this? Well, so the way Hilden proved this fact about three manifolds being branched covers is he basically fixed a standard simple threefold cover of the genus G surface over the two sphere. And this is sort of a picture of what his cover looks like, right? So you take a sphere and you know, on the boundary, you fix 2 points that get sent to one of the transpositions in S3, and the rest, and then you pick some even number of other points that get sent to the other transposition S3. And when you look at the threefold covering corresponding to this branch data, you get this sort of strange looking genus 2 surface. And this is maybe it's not clear based on how this drawn is whether this is a branch covering of surface or a handle body, but that's actually kind of the point, right? So maybe I'll just, I don't know, maybe I'll just say, you can sort of extend the branch covering of the surface to a branch cover of a handle body by connecting these points in pairs. Actually, maybe it would be more elegant to do it like this, right? So this branch covering over the surface extends over the sort of standard handle body in this nice way. But Hilden actually proved something much stronger by considering the mapping class group of this mapping class groups of surfaces. He proved that given any handle body, if I start with this fixed branch covering of a surface, and I consider any handle body that I can think of as being bounded by that surface, then there's an extension of my branch covering across that handle body.
Question. What were the arcs that you just drew? What did they represent?
They are meant to indicate that I can think of this. So on the right here, I can think of this as a ball, which I can think of as sort of like the top disk and the bottom disk, the top disk cross I. So like this point goes to this point when I cross with I, and this point goes to this point, this point goes to this point, this point goes to this point.
Oh, okay. Thanks.
Yeah, or maybe just more simply, these arcs are just ways of extending the branch covering across a trivial tangle, right? And if I just started with this branch covering of the sphere and I wanted to extend it over a ball, all I need to do is connect the branch points in the sphere with trivial arcs in the ball, and then I will have defined a branch covering over the 3-ball branch along those arcs.
So just to make sure I'm seeing this picture correctly, so I take the thing on the right, I think of like a pillowcase or some kind of weird cut, and I take 3 of those.
That's right.
Take one of them, I slid it along the yellow line. And
yes, I think it's useful to think of cut open all 3 copies along arcs connecting the points in pairs. So then you get 3 4-punctured spheres.
I see, and then I take 2 of them and glue them together along the red arcs to make the bottom 2/3 of the donut, half donut thing. And then I stitch another one on the top right. Okay, I think I can see that. Yeah.
Yeah, and again, the stitching is controlled by the monodromy representation. So if I call this point 1, and then the 2 is sort of hidden back there, and the 3 is here, this is consistent with saying that these arcs are getting mapped to 1, 2, which means that in the 3rd sheet, I just sew that stitch back up.
Right.
And then the other one is getting mapped to 2, 3, which means in the 1st sheet, I just sew those 3 stitches back up. But in the 2nd sheet, I need to keep both of them open because they transition to another sheet. Does that make sense?
Can I ask something?
Please.
I'm not getting the red arcs on the right-hand side of your pillowcase or whatever.
Well, so choose any arcs connecting those points, right? That will give you an extension of the branch covering of the surface across a trivial tangle. Right, so I'm defining these. I don't know why I did it, but I did it. So now I have to explain it. I mean, I'm drawing this trivial tangle in which, because it pairs points that have the same monodromy representation, I can extend the monodromy representation across the trivial tangle.
So I should think of those red arcs as living inside the ball?
Sure, yeah.
In that pillowcase presentation? I see.
Yeah, and I mean, yeah. This is kind of one of the things about trivial tangles is sometimes when you draw them, it looks like the arcs lie in the boundary, which is of course the point because trivial tangles can be isotoped to lie in the boundary.
I see what you're saying, but you want to think of them and as living inside that ball, so they're going to be inside the handle body. Okay.
Yeah.
Maybe.
Okay. Great. Yeah, I think I'll move on. Okay, so let's just look at this fun example then. So here's I've drawn in the monodromy representation for a bridge splitting of the trefoil. And what we notice is that so just ignore the stuff on the right for now. So what I want to point out is that if we just look at the bridge sphere, this is a 2-sphere branched along 4 points. But if we think about sort of this maybe we think about the 4-ball below, right? This 4-ball below is really just this disk I drew earlier crossed, actually both of these 3 balls, both of these trivial tangles are just a disk with 2 points crossed with I. And we saw earlier that the covering of this disk is again a disk, right? So what that tells us is that the branched covering of this bridge splitting is a Haggard splitting of genus 0. Because the ball below the Haggard surface lifts to a sphere, the ball below the Haggard surface lifts to a ball, and the ball above, or ball below the bridge surface lifts to a ball, and the ball above the bridge surface lifts to a ball. Right, so the point is that the trivial tangle on 2 strands with this monodromy representation is covered by a 3-ball. So this gives you just a quick proof that the 3-fold cover of the trefoil is actually the 3-sphere. Which I think this was at least counterintuitive to me when I first started learning about this stuff, because I was like,
every 3-fold cover or this particular 3-fold cover?
This particular 3-fold cover, which is the only 3-fold cover.
Oh,
In some sense. I mean, the trefoil group doesn't admit so many
right.
representations to S3. To
What about every 3-fold cover of every 2-bridge knot?
Yeah, exactly. Every 3-fold. Yeah, if the 2-bridge knot admits a 3-fold cover, meaning if it's 3 colorable. Yeah, so this is, Sasha is the world expert on saying this, but like, in fact, any dihedral cover of a 2-bridge knot will be S3. I hope that's right. Okay. Okay, so this is the first point in time where we can start thinking about, so the way I was thinking about this is we start with surfaces, branch covers surfaces, and then we have these results that tell us sort of we can extend across handle bodies and trivial tangles. So now we're talking about 3-dimensional objects. And now we want to think a little bit about how we can extend across 4-dimensional objects. And there's going to be 2 main ways this happens. One will be across cones, and one will be across these trivial disk tangles that we use in the definition of bridge trisections. So if we let D be the cone, now I'm over here on the right. If we let D be the cone on the trefoil in B4, then we can extend this branch covering F to a branch covering from the 4-ball to itself, where the branch locus is D. Okay. And in fact, this branch covering could be described very elegantly in coordinates. If we think of the 4-ball as the unit 4-ball in C2, we can describe it in terms of this nice function right here, which is known to geometers as the cusp singularity. Okay, and so this shows up in complex manifolds and symplectic manifolds. And I think I mentioned in the abstract that I would maybe say something about the work with Laura Starkson and Peter Lambert Cole, but I don't think I'll say too much other than this is the sort of singularity that comes into play in the work of Aru and Kartsakov. Katsarkov. Okay, one of those. All right, and this is more general, right? So whenever we have a link with a branch cover to S3, we can extend over cones in this way. So the cone on S3 will be the 4-ball, and so we'll have a branch covering with a 4-ball over the 4-ball, where the branch locus is the cone on the link. Okay. All right, so the other useful example to keep in mind is the unlink of some number of components. So here's an unlink of 3 components in 4-bridge position. And the simple fact here is that the genus G Haggard splitting of the connect sum of K copies of S1 cross S2 is a G+2 bridge splitting of a K+2 component unlink. So I guess the covering space here would be S1 cross S2. And the Haggard splitting would be a genus 2 splitting of this standard manifold. Okay. So, okay, what's the point? I mean, we know from Hilden, Hirsch, Montesinos that every 3 manifold is a branch covering over some knot or link. So we know that's true of these very nice 3 manifolds. So we can sort of think about what might kind of links might show up. And of course, the answer is pretty simple. And what's useful about this is, from my perspective, is that these unlinks are the boundary of trivial disk tangles in the 4-ball. And so if we have this sort of branch covering on the boundary link, then we can extend it over a trivial disk tangle. You can just extend the monodromy representation over the disk complement. Okay. All right, we're getting somewhere. Okay, so I think this is the last sort of, let me look ahead. Oh, yeah, there it is. So this is the last sort of like key ingredient in our theorem. And then I'll finish the talk by walking through the sketch of the proof of our theorem. But so one thing that hasn't really come up in my talk so far, except I sort of just alluded to it in the last slide, which was that now that we know every, say, 3-manifold is a 3-fold cover over another link, we can ask, when can we relate to such coverings, right? Or maybe you could ask it in terms of which links can be the branch locus of a given 3-manifold over S3. And this question was posed by Montesinos and then answered by Pirgolini. And it was actually a little bit of work for us to extract this theorem statement from Pirgolini's paper, because he worked with Heegard splittings, but he actually doesn't have a theorem statement in his paper. And the thing that, it's clear what he's proving, but it's not this. And it's just some fact about 3-manifolds. But anyway, if you keep track of the Heegard splitting structure that he's working with, this is sort of one way you can phrase the theorem. So let's see what this says. What's the setup? Basically, we have 2 3-fold covers of a homeomorphic, let's not worry about the identity map or things like that here. We have 2 homeomorphic Heegard splittings. And they're each realized as sort of a 3-fold cover over a bridge splitting of a link in S3. And so what he proved is that there's a set of moves that one can do to convert like half of this bridge splitting into, so this tangle T2 prime into a new tangle T2 double prime, so that the resulting link is isotopic to the other link. Okay. In other words, if we have these 2 bridge splittings and we know that their 3-fold covers are homeomorphic as Heegard splittings, there's actually a calculus of moves we can do to modify one of the tangles until we get something isotopic to the other.
What's the title of that paper?
Moves on branch coverings or something like that.
Something covering moves, something.
Covering moves, yeah, covering moves something. Good.
And is that isotopy, does that preserve the bridge splitting, or just that the links are isotopic?
That's a good question.
Or maybe you don't care.
Well, we tried to figure out the answer to that question. I think we couldn't. But we didn't care, so we moved on.
All right.
But it's a good question, actually. And yeah, it just wasn't, maybe Saskia can correct me, but we actually talked about this a lot. And I think we couldn't figure out to what extent this link here, to what extent L double prime is isotopic. So we know that they're isotopic as links. I don't know if they're isotopic through bridge splittings of links. And actually, I think I decided that maybe the answer is no, in that if you just swap out different bridge splittings of unlinks, I think it's not super clear that they should be isotopic. Well, they're not isotopic to bridge splittings, but it wasn't clear you could do moves in any meaningful way to achieve that. So that's actually an interesting question, I think.
Okay, can you slow down again? So what you have is 2 different links, L and L prime, together with bridge splittings that give you the same Heegard decomposition of some 3 manifolds, right?
Yes.
And then you're saying there's some sequence of some particular kinds of moves that transport one bridge splitting to some 3rd bridge splitting, where this 3rd bridge splitting is no, not just the bridge splitting, just that the 3rd guy is isotopic to L, but not with the bridge splitting.
That's right. That's exactly right.
But you do need to know that the moves only happen on one side of that bridge split.
That's right. That's why this is so clumsy, right? The point is we want to be able to do the moves away from the bridge sphere, fixing one of the tangles. And this is absolutely crucial. Yeah, good point. Yeah, and I guess, by the way, I mean, it doesn't have to be a secret. What, the main move that factors in here is the so-called 3 move, right? Which looks like this. So somewhere in one of your tangles, you might see, how's it look? Something that looks like this, right? And what you're allowed to do is you're allowed to replace this with, or either replace this or create it with this, this local change. And so Montesinos knew about this. He knew you could make this sort of local change. And Pirgolini basically leverages this into, I think four moves in total that suffice to go between any pair of links. So, I mean, the simple statement of Pirgolini's theorem is that if 2 links have homeomorphic 3-fold covers, they're related by a sequence of these moves. So it's a much simpler statement, but we need to keep track of this bridge sphere. Okay. Should I stop, or should I go to I should know how long these talks are.
Sorry, you should keep going. You
Okay.
should talk till the end of the hour.
Okay.
If you feel like it.
Okay, so I think we're on track here. So let's talk through the proof of the main theorem. So what do we want to do? We're given a trisection where one of the parameters is 0. And for whatever reason, I've decided to make that parameter the second parameter now. So this is the schematic picture of the trisection we're given, and this is the schematic picture of the trisection of S4, together with some useful notation. And what we'd like to do is we'd like to build a 3-fold cover between these objects. Okay, so the way we do this is we first build a 3-fold cover between the cores of these objects. So the core of the trisection upstairs is just sigma, some genus G surface, and the core downstairs is S, which is the 2-sphere. And so the map we pick between these is Hilden's map. So we essentially identify the core upstairs with the standard genus G surface, identify the core downstairs with S2, and then we get this branch covering that Hilden gives. It's the explicit branch covering that I showed you a little while ago. Okay, and then we apply Hilden's result that branch covering can be extended across any handle bodies bounded by the surface. So upstairs, we have these 3 handle bodies bounded by the surface, and Hilden tells us we can extend F to get these little F sub I, which are branch coverings from the handle body HI over the 3-ball BI with branch locus some trivial tangle. And the other thing to remember, all this won't be important until later, Hilden actually gives us the flexibility to sort of choose the way a trivial tangle gives you a pairing of its boundary points. And what Hilden tells us is we can actually choose the tangle in any way to pair those points in any way we want. So that will help us control things like connectedness of the pairings of these tangles. Okay. So the problem here, though, is that
wait. So you don't have to connect blue points to blue points and red points to red points. You can just do whatever.
Oh yeah. So there's the opportunity for confusion here, which is that the red and blue and green on this slide do not correspond to the monodromy representation like they did on previous slides. There's no 3-color. I'm not 3-coloring the pieces of my trisection or anything.
Okay.
So that's how I interpreted how I should answer your question. Sorry. Does that make sense?
That wasn't really the question, but doesn't
No,
matter.
but okay. So yeah.
I'll ask you at the end. Okay.
No, I'll flash back, Gordon, to Hilden's map, right? So we do have these sort of distinguished red and blue points, branch points, right? And
Right.
Hilden tells us that we can build tangles, but what he tells us is that we can connect, say, the red dots in. So actually, I see where you're concerned. You're saying why can I connect it like this?
Yeah.
Well, if they link, I can do that. If there's something. So now think about my move here, right? So here the red goes to the red and the blue goes to blue, but look what happens when we add in the 3 move. I've changed the parity of the way they pair up. I can do this with knotting. But I need to do something. I need to be conjugating my meridians in some non-trivial way in order to do the thing you're worried about. But it can be done. I mean, this shows you, here's a pairing, and then here's the opposite pairing. Right? So this shows you can basically transpose pairings with a 3 move.
Okay, but there is something to think about what you can and what you cannot do.
Yeah. So yeah, exactly. And
Maybe
yeah,
you can do everything, but you have to argue why. Okay.
yes. Yeah. No, it's not trivial. That's right. Okay. So again, the problem is, so we've got these trivial tangles here now, but the problem is that pairwise, they might give us really complicated links, right? So this is some link, and this is some link, and this is some link. And I'm happy coning this one. I'm happy coning this link off because the 4 manifold that's sitting above it, Z2, is a 4-ball. So I can extend this, I could extend this across the 4-ball by coning off here. That would be fine. But I don't want to cone off here because I don't have 4 balls sitting up above those pieces. So what I need to do now is I need to fix these 2 links so that I can cap them off with trivial disk systems, trivial disk tangles. So to do this, we apply Piragolini, right? So we apply Piragolini to this link, T1, T2, to change. So we want to change it into an unlink, right? So why can we change it into an unlink? Well, we know that this is some link whose cover is connect sum of S1 cross S2s. So by Piragolini's result, there's some moves we can do that are going to be supported in tangle 2 that will give us a new tangle 2 so that the union is an unlink now, or isotopic to an unlink. So that fixes this sector. And then we do the same thing for this sector because we didn't change tangle 1. So now we can modify tangle 3, right? So we change this to tangle 3 prime and change this to tangle 2 prime. Now these are unlinks. Because the covering manifolds were connect sums of S1 cross S2s, we knew there were sort of Piragolini moves that we could affect in this tangle and this tangle to turn them into unlinks. And this is why it was so important that we sweated the details of Piragolini, because we needed to fix this tangle. We wouldn't want, we wouldn't want to make changes to both of these to get an unlink and then go make changes to these and mess up this one again. Okay, so then how do we finish the proof? Well, since this is an unlink, we can extend over trivial disks. And this is an unlink, we can extend over trivial disks. And then this is some complicated link that we have no control over. And so we extend over a cone, and that lets us extend over the 3 pieces upstairs. So we started with the branch covering of the cores, we extended over the spines, then we fixed it on 2 parts of the spine, and then we extended it over the sectors.
And so now you have this new link on the left. How do you know that the cone thing is still B4?
Right, well, the boundary link has as its branch cover S3. So we can just take the cone on that branch covering, just like we did with the trough wall. Okay, and then maybe I'll just note quickly, if you wanted to get cones on knots, what do you do? Well, now we also know that K3 is 0. So what we do is, instead of fixing these links, or we still fix this link, so we get an unlink in this sector again, we can extend over disks. But now we change the extension, or we change the tangle in this arm of the trisection. We affect the pairing of this tangle so that these become links. And these become knots, and then we cone them both off. And we see we can get 2 cones now, because now this is a 4-ball and this is a 4-ball. So now we're sort of allowed 2 cones. And in fact, I think you could make another another modification of this. If all the parameters are 0, then you could get 3 knots without any work at all. You could just change one of these. You could change 2 of these so that all 3 of the pairings give you knots, and then you'd get this sort of 3-cone object.
Hey, let me ask another stupid question. Before they were links, why do you now know they're not?
Well, because we're doing something different, right? The final step here is, so yeah, maybe I'll just walk through it one more time. Everything's totally uncontrolled, and then we change this one so that this is an unlink.
Right?
And instead of changing this one so that this is an unlink, we change this one so that this and this are knots, and this are knots. But more
Okay,
grammatically.
okay.
Okay. And
So,
I think
sorry, in this last step, so you need to prove that you can make it not, or is it automatic?
yeah, we use Hilden to claim that we can pick this third tangle so that it induces a pairing of its bridge points that forms a knot with both of these tangles. There's actually there's an argument to be made that that's possible. But yeah, and there's actually a clever bridge trisection argument that it works. You
Okay,
basically just need the existence of certain types of bridge trisections, and then you know that there's such a pairing.
Okay.
Okay,
thanks.
I'll stop, and I'll just change to this page, which shows that we can actually sort of draw these coverings explicitly in some cases by coloring sort of singular bridge trisections. And I can talk more about that, but I think I'll stop for now. Thank you so much for your attention.
Unmute there. Thank you, Jeff. Do you have to run right away or to teach?
Oh yeah, I have class starting.
Do you have time for questions?
No, I'm late for class. I gotta go.
Oh shoot. Okay. Well, Sashka will answer all your questions, and let's.
Oh, that'd be great. I'm sorry. Yeah, I wish I could stick around. I totally forgot.
Sorry, we made you late for class.
Wait, can you send Sashka your talk so we can flip her back?
I could try to. Yeah.
Yeah, you can post it in the chat.
But don't be late for class. You're already late.
Yeah, I'll try to do that. Okay. Bye, guys. Thank you.
Bye.
Bye.
I was serious. Any questions for Sashka? Oh, there's dog.
Oh, there is a dog
Yeah.
competing with my cat, but my cat went to sleep, and I'm not gonna wake him up.
It's no photo. I mean, it's a dog.
It's the best dog.
There is the sleeping beauty,
Mm. Oh yeah.
but you can't see him because there's backlit, right?
There's a well ordering, and all cats are above all dogs, so it's kind of clear. I can, in principle, try to answer questions. I mean,
Actually, I didn't want to ask questions because I didn't want to throw them down, but almost last step. There's you mess. So there's blue, green, red, and you mess with blue, so the blue green becomes an unlink.
mhm.
So you can cone it off, and then you mess with red, so that red green becomes an unlink.
Mhm.
And this is Gordon's question. How do we know that we didn't change the three manifold that is the branch cover over blue?
Well, because when you
red.
make the moves, you always so this was relying on
You have to
you
know what
doing
the moves
the
are.
where you start with two homeomorphic Higard splittings,
Mhm.
and you make moves on the branching set which preserve the total space. So not only are you fixing one of the tangles, but you're also fixing the other handle body.
Oh, I see. You really are. Yeah. Okay. So just
You're not really. Are you really fixing it, or are you just saying it's the same kind of handlebar?
Yeah. Well, fixing it in the sense that when you take the branch cover after you have modified the branching set, you get the same result.
In other words, it should be that the same curves bound discs. I mean, we want to know that we want to know when you glue those two handle bodies together, you still get S3.
Or whatever manifold it is.
Or whatever manifold it is. Well, yeah. And so, but the point is that we were modifying this in order to fix this, and then we modified this in order to fix these two, and now we need to know that those modifications of these two things didn't change.
Fits together somehow, right?
But it's because just this modification, those moves you're saying don't change the corresponding handle body filling
Mhm.
of surface upstairs. Right.
Yeah, and I guess a good sort of analogy to have in mind is your observation that any two bridge knot will give you S3. So Jeff did the trefoil in detail, but actually any two bridge knot would give you the same result. So you can think of, if you take a bridge splitting of the trefoil where one half is just like the standard picture of the trivial tangle where it's just like two cups, and then you fixate on the other half and you change it to any arbitrarily complicated two bridge knot, the result will be the same three manifold in the cover. So you have a lot of choices for that tangle.
And you're not arguing that you didn't change the knot that we're going to branch over, but just that,
We intend to change the knot.
right, you have
Because we
changed
started-
actually the knot, but not the handle body splitting of S3.
Mhm. Yeah.
I mean, not the fact that it is S3.
Well, not the fact that it is whatever manifold it was. I mean, in a lot of
To
these.
start with, right?
Yeah.
Yeah. I mean, in this case, yeah.
Mhm.
I mean, I sort of understand the Piergalini's theorem that says I have this guy, and so I mess this and fix this. I mess up this, and it's still the same manifold I started with, and I've actually gotten the thing I wanted to get, right? That's the theorem.
Yeah, that's, yeah.
And I messed with this, so I didn't touch this guy, so he's there. And now I go up there, and now I mess with this guy to fix this. But
You had it almost right. So okay, so you start, you fix this guy, you mess with this guy
right.
until you have an unlink. Okay.
Right.
Now
Mhm.
you go to the third one, you still fix one, you mess this one, but what you want to fix is this part here.
But that wasn't, I mean, the way he did it. So the way he did it, that this thing on the side was the thing we wanted fixed. And we were messing with the two things
Right,
that
yeah. I'm just
one above
saying,
the other.
well,
right?
I guess maybe okay, I don't know, I guess I'm not doing a good job with the body movement, but what I mean is, if you look at the trisections upstairs, the parts that you want to fix are the parts that correspond to handle
B3.
bodies of higher genus. So you have two handle bodies of positive genus and a four ball.
Right.
And the game is that for the four ball, you don't care what kind of branching set you're getting because you're gonna cone it off anyway. So what you want to do is you want to fix the other two branching sets until they become unlinks. And that's possible because the cover of an unlink is
Right.
something like some of S1 cross S2s, and you can apply Piergalini. So you fix these two parts because for an unlink, you can extend over trivial disks. And then for the third sector, it's a messed up link. Can't do anything about that, but you can cone it off.
Well, how do you know that when you branch over that link, you're going to get a ball upstairs? A sphere upstairs? When you change that link, right?
Right, but so how did we